Last talk of this morning's session is volumetric ultrasound imaging with capacitive micromachined ultrasonic transducers by Pierre, Khuri-Yakub, Stanford.
Thank you. First of all, let me thank also the organizing committee for inviting me to come and talk to you today about the work we're doing on capacitive micromachined ultrasonic transducers, and especially as it relates to 3D ultrasound imaging. So to start with, I want to spend a few minutes telling you what a CMUT is, and then talk about the various technologies that we need to develop or that we have developed along the way to try to do 3D real-time ultrasound imaging. And then I'll close by showing you a few examples of 3D imaging with 16 by 16, 32 by 32, and ring arrays for various applications, including for acoustic imaging. So what's a CMUT? Well, it's a capacitive transducer, capacitive ultrasonic transducer, and it's typically made looking something like this. You have a lot of cells. Each one of these circuits is a cell, and each one of these circuits is an individual capacitor. And so it's a plate that is vibrating over a substrate with a gap in between, and the characteristics of the cell basically dominates the total performance of the transducer. A transducer or an element is made by putting a number of these in parallel. So electrically, they're all in parallel, and because this is all done by photolithography in an IC fabrication facility, anything you can draw, you can build. So you can make single element like I'm showing in here. This is a HIFU device. You can make 1D arrays, 2D arrays, ring arrays, whatever shape device you want, you can make quite easily. What makes these devices work is the high electric field. If you want to compete with piezos with high electromechanical coupling coefficients, what you need to have is large electric fields in the cavity, and once you have large electric field in the gap, that automatically translates into a high electromechanical coupling coefficient. And because it's done with IC fabrication technologies, you can go in frequency anywhere from kilohertz to 100 megahertz, and the size of a device can be as small as 100 micron by 100 micron, which is what we made, up to a 4-inch wafer, which is the size of the wafers we can use in our facility, but you certainly can go bigger than that. And if you use flat panel display technology, you can make devices as big as a window, if you wish. And the other very important advantage is that, in effect, we're giving everything back to silicon. So you saw earlier today talks about the influence of computing on how you do things. We're turning the transducer into a silicon thing. So the transducer is silicon, the front-end electronics are silicon, the back-end electronics are silicon, the display are silicon, the whole world is silicon. So you can imagine an array on a wafer with all the electronics underneath it, and the display and everything, and solar cells, so that you don't have to plug it into anything. You just throw it on somebody and you're done. So it's giving really everything back to silicon. Now, in terms of technologies for making CMUTs, we've developed two types of technologies. One is called surface micromachining, one is bulk micromachining or wafer bonding. And the idea in both of these is to make some cells like this with a vacuum cavity. And the two technologies have been well described in the literature, so I'm not going to spend a lot of time on them. The important differences between them are that with this technology, there are no limits on the dimensions of the devices we can make. This type of technology is mostly limited to what we do in medical ultrasound imaging. With this one, for instance, we can go all the way down to 10 kilohertz or 20 kilohertz, which is very difficult for us to do with this sacrificial release technology. We also had to develop through-wafer via technologies, and the reason for that is to allow us to do 3D integrations with 2D arrays, because if you have a fully populated 2D array, you don't have enough room or space to make routing for metal lines to connect to the electronics. So we developed a through-wafer via technology in order to do this, and that allowed us to do the integration through flip chip bonding or direct bonding here. Flexible arrays refer to the fact that because this is silicon and you can etch it, you can then fill the etched spaces with a polymer like RTV, and then we've made arrays that we can wrap around the 1 millimeter needle or a 3 French catheter, for instance, quite easily. So there are a lot of possibilities of what you can do with the technology. In terms of comparison with piezoelectric transducers, I would say the main difference right now, or the main disadvantage that we have right now, is that piezos are linear in their operation, whereas CMUTs are inherently nonlinear because the force is proportional to the square of the electric field. And so there is nothing you can do about the nonlinearity. There are people who doctor the electronics in order to reduce harmonic generation, but this is a fact of life with the CMUT. Other than that, I think we're competitive in every respect. And one of the very important aspects of the CMUT technology is the thermal budget. So piezos have dielectric loss tangents, which makes them get heated as you use them for HIFU, for instance, or even in traditional imaging, where there are no loss tangent in a vacuum gap, and the silicon as a material has very high Q, so there are no internal losses, and so in terms of thermal budget, this is very important. The fact that it's lead-free is another aspect of the technology that you want to keep in mind when eventually people will not allow anybody to use lead in anything. In terms of integration with ASIC, it's very important because now we can make things in silicon. It's very important, especially when you make 2D arrays. You end up with devices with small capacitance, whether it's piezo or CMUT or anything. And a 1 puff capacitor is not going to drive a 2-meter cable with 150 puffs. You're just not going to get enough signal at the other end to do business with. So integration is very important. And there are different approaches to integration. You can do through-wafer vias with solder bumps, connect to a printed circuit board or to the ASIC directly. Or you can do directly bonding the CMUT or doing it by the surface micromachining technology I showed you earlier directly on top of the electronics. Either one of these two works. There are some very interesting advantages if you want to think about fancy things to do when you actually have an electric contact inside every cell. So not only can you apply phase differences on element by element to the imaging, you can apply phase differences cell by cell to play a lot more games. So there are a lot of interesting potential that you get out of this. However, when you do this integration with electronics, you have to keep in mind this idea of power consumption and thermal budget. Because we can easily, and I'll show you, we've made 128 by 128 element arrays in 1999. That's 16,000 elements. If you integrate them directly on electronic channels and each one of them consumes 10 milliwatts, you're talking about a lot of watts. And this thing becomes a soldering iron or you start cooking people and not really doing any medical imaging on them. So it's very important to keep track of this and then recognize that sometimes you may want to use an interposer in between the CMUT and the electronics just to alleviate the issue of the power consumption that you need to handle. And the final thing we had to do, which is not something we started doing when we tried to develop this technology, is that if you build a 2D array and you want to do 3D imaging, you can't buy an instrument out there to do 3D imaging. What you buy from GE, Siemens, and Philips and others for 3D imaging, they give you 2D arrays with a handle that contains ASICs that are specific to their system. So you are stuck with that. And if you have a 2D array from scratch, you cannot use an existing commercial instrument to do your imaging, so you have to do your own thing. And so that led us to purchase something like this Verisonics platform, which then allows us to write our own code and develop, for instance, a beamforming for a ring array, which commercially does not exist at all, and also to do 3D, 4D imaging, because we needed to do it with our own specific ASICs ourselves. So now let's see what we have done with this. So in terms of, for the CMUT, we have a number of different applications in medical imaging, and today I will focus on 3D anatomic, and I'll show you a little bit of photoacoustic imaging also that we're doing, but we're doing other things with it, and then we're doing a lot of airborne ultrasound applications with the CMUT, and this is becoming very interesting and important right now, and that's the idea of doing imaging in air, instead of medical imaging inside the body, and detect people and gestures, and allow to do man-machine interactions simply with ultrasound instead of just with optics. And there are advantages there also. So now we come to 3D imaging, and the first thing we have to face is the fact that nobody's going to allow you to bring a probe with 1,000 cables. And from carpal tunnel syndrome issues to weight issues to other kind of restrictions. So that's why the commercial vendors today do business inside the handle. And so we had to deal with that also as we started going up the curve of making large element arrays. And so we have to come up with different solutions to this problem. There are people who are working on XY addressing to reduce the number of cables that access the 2D array. And we're looking at a different solution, and the solution we're looking at is shown in here. So our approach to doing this is to compare the classic phased array and its performance in terms of resolution to what we call full transmit X receive, where we receive on the diagonal elements on the array and we transmit on the remaining elements. So we have some elements that are dedicated to transmit and some elements that are dedicated to receive. And then the important thing is that we can program and build an ASIC with a transmit beamformer where we don't need 224 cables to address the 224 elements. We only need 8 control lines to plug in the phase delays to the various elements and do the phasing to do the transmit beamforming. And that, like for instead of 256 elements, for instance, in here, we use 32 plus 8. That's 40 elements should be enough to come down from 256. And so this is what we've done. First, I wanted to show the 128 by 128 array, which we did in 1999 for an AV program for underwater diver camera. And then 16 by 16 array is shown in here. This is the CMUT array. This is the ASIC with transmit beamforming that's connected to this. This is the digital part of the chip where we do all the delays and the control signals. Underneath this, we have the protection circuitry, pulsars, and receive preamplifiers for the diagonal elements. We can also tile 4 by 4 of these to do 32 by 32 real-time imaging. So the CMUT are tiled on one side, the ASICs are tiled on the other side. But we also have 32 by 32 CMUT arrays. This is an ASIC that we have designed, and for electronics, we have very good relationships with electronics companies. When we started Analog, now TI, was providing it with ASICs for free. We just design them, take them out, the tape out gets sent to them, they fabricate them, send us the dies, finished, and we don't pay for them. When we asked National to do a 9.2 millimeter by 9.2 millimeter die, they refused. It was too much real estate. Intersil stepped up to the bat. And so now we have this design submitted, and we expect it to get by the end of September. So in October, we'll have these two flip chipped on top of each other, and then we'll have 32 by 32 real-time imaging with just a simple device instead of tiling 4 elements with respect to each other. We also recently developed a relationship with Maxim, and Maxim is also more than willing to provide us with these types of ASIC and even more, actually. So this is 3D now real-time imaging at 5 frames per second. And this is limited right now by the data transfer between the Verisonics and the PC. This is a phantom for a ventricle. This is a spring. We like springs. And so this is real-time 3D, and the images have been slowed down to show them to you in here. Now, in terms of photoacoustic imaging, you saw a very nice introduction of what photoacoustic imaging is. You shine a laser, you get absorption, thermal expansion, and emission of waves. And this is the first example of what we did with real-time imaging with photoacoustic. Here we have a 16 by 16 2D array. We place it over a phantom with a number of wires with different materials inside these tubes, actually, from water, ICG, blood and ICG. And the idea is that with the anatomic imaging, you see all the 4 tubes in there. with for acoustic imaging, you only see the ones with the contrast agents, namely the ones with ICG, blood, and blood plus ICG. The other aspect of this demo that is not very maybe clear in here is that these tubes were 5 centimeters away from the light and 5 centimeters away from the array itself. So we look at the 5 centimeter penetration of the light with the absorption and scattering, and then 5 centimeter propagation to the 2D array. Now this is really what I wanted to show, and that's the fact that we're collaborating with Professor Sam Gambier, and one of his postdocs is working in my lab, and we're building a transrectal photoacoustic imaging device, prostate probe. And the idea is to take one of the CMUT array that I just showed you. We started with the 16 by 16. Later in the year, we'll do the 32 by 32. This is the front end A6 in here, it comes out. And a bunch of fiber comes from the side of this. As you see in here, these are the end of the optical fibers. This is the 2D array, and this is the sort of the prostate probe, let's call it right now. And this is it here sitting in the lab, and this is a prostate phantom. And that's shown in here. This is the rectum, this is the prostate phantom, and at different distances, up to 4 centimeters above the rectal wall, we've put different contrast agents in there, and these things are imaged in real time, and we look at the superposition of the photoacoustics and the anatomic images on top of each other. And this actually was supposed to be a movie, but I couldn't find the movie in the computer, but it's basically showing you the same thing. And I'm told Raj tells me that Sam wants him to start doing human trials with this, and I tell him not in my lab. So we're acquiring another OPO laser that they can use in the clinic to do human testing. We've had a lot more data actually on human prostate that were excised, put in gels and on agar gels and tested in the lab, but I don't want to show those results yet. The last example I want to talk about is ring arrays. Ring arrays, by definition, are two-dimensional, so you're looking at 3D imaging. These were developed for intracardiac echo to guide catheter for arrhythmia, for RF ablation with arrhythmia. And the nice thing about an annular array like this is that you have a lumen in the middle, and through this lumen you can do a lot of things. You can bring lasers for photoacoustic imaging, you can do lasers for ablation, you can do ultrasound ablation, you can do biopsies, you can do anything that you really want to do. And so what we have built is a ring array with 64 elements, forward-looking. You see the black dots in here are the through-wafer vias to bring contact to the CMUT element, which is 100 by 100 microns, roughly, to the back side. And then this is integrated in the following fashion. This is the CMUT array in here that's flip chip bonded on a flexible PCB with 8 legs. Each one of these is an ASIC with a protection circuit and preamplifier. These are flip chip bonded themselves onto this octagon, onto the flexible PCB. The ASICs are also thinned down, so they're only 100 microns thick. And then this is all folded over this alumina backing in here, and then it gets sent to Tyco for cabling. It gets sent to St. Jude for turning it into a catheter, and this is now the full catheter, and this is the ring array in the front covered with PDMS or Silgard actually on the front, and the hole in the middle you can see the RF ablation probe coming out of it. For this we had to do our own development for beamforming to display 3D images. And this is one game we're playing, is that what you see in here, we look at the plane above the ring array, and then we rotate it at 10-degree increments or 5-degree increments. And what I'm showing in here is the spring as it's displayed and maximum projection on the plane. And we're looking at the projection as the plane is rotated across to give you the good sense that this is a 3D structure, that this is like a stent or a spring that you're actually looking at. This is now out of an animal study we did almost a year ago right now, and this shows it's inside the heart, and you're looking at 3 different planes, and you're looking in here at a 3D rendering at the endocardial surface. We need to talk to the cardiologist to learn more about these things. So in conclusion, we have a platform technology. We do a lot of medical ultrasound imaging, 2D and 3D with it, and therapy. There are a bunch of people who do all the work and people who fund us to do this research. Thank you.
Time for a few questions.
It's very nice that you can put everything on a single chip. But what about mechanical cross-coupling between CMUTs?
Mechanical?
Cross-coupling
Between what?
between different CMUTs.
Okay, so that's a good question. So there are a number of different sources of coupling in transducer elements in general, whether it be piezos or CMUT. So if you compare them side by side, actually piezos have more coupling, lateral coupling, than CMUTs do. The biggest source of coupling in transducers is usually the interface mode that propagates along the surface between one element and the other. You can also get coupling through the substrate, but that tends to be quite weak. The coupling that goes through the surface or interface mode between piezo and water or CMUT and water are typically damped with the matching layer that you use when you put 1D arrays on them, which is like Silgard, which are quite attenuative. And you can do the same thing with 2D arrays, having a thin layer of polymer, which is attenuating. You end up with a lot less crosstalk. Actually, CMUT are very good at preserving the large acceptance angle at frequency. So even if you take two arrays and you benchmark them side by side, a piezo and a CMUT, with the same aperture, the lateral resolution at the same frequency of a CMUT array is better than a piezo, even with the same aperture. And the reason for it is because you retain the high frequency acceptance angle. That makes sense?
Question about
yes.
Implementation. What voltage drive do you need to get the IE field to jiggle the CMUT?
You can do it with 10 volts.
10 volts?
Yes, I mean I had a visitor from an EEC who wanted to build CMUTs. We demonstrated this full integration with electronics, and they were looking at using more than 10 volts. So no, but I mean the reason for it is you want to ask yourself, how many megapascal do you want on the surface? How far do you want to go in? And what's the gap size? And so if you don't want to go too far, then your gap is 1,000 angstroms. It doesn't take very much to get a 10 to the 8 volts per meter electric field across the gamut. Yes?
Would you ever see using this in to thermally heat tissue, or would that much power, like if you deliver a lot of power, would these things hold up to that sort of strain, such as like HIFU or something like that?
So I think HIFU is easier for us.
It's easier in the...
Yeah, I mean there is a reason for it. So HIFU, you see, with a piezo, when you want to do HIFU, you have to water cool it to keep the temperature down to 60 degrees or something. These guys don't need that. So that's part one. When you're exciting a transducer to do imaging, what people tell me they want 2 or 3 megapascal output pressure at the face of the transducer for imaging. For HIFU, you need only less than a megapascal typically, something in the 20 watts per square centimeter range at the face of that. So the difference is not the total absolute value of the pressure that you need, it's the fact that one of them is quasi-CW and one of them is impulse excitation. In HIFU, the tissue that you get comes about from the focusing gain, from the F number as you come down to a focal spot and get your watts per square centimeter in there. So the only question then really is the ability to handle current. And so the way you handle current is either you make your metal very thick, so you don't have to worry about electromigration or erosion, or we use thick silicon plates that are highly conductive, and now we have 6 microns of silicon or more that carry the current, and that goes away completely. So the issue is really there is no issues from the fatigue, mechanical fatigue, if that's what we're concerned about.
Just overall.
Yeah, I think overall, we only see failures in CMUT from electric field.
Okay.
It's the high electric field that makes it, it's the high electric field that breaks it. It's as simple as that.
Yes. Given how robust they seem to be, have you ever blown up one of your CMUTs? Does it take effects?
With bullet? No, just no, it takes electric field. So with the electric field, they're very easy to break. You just keep turning the knob. I mean, you just keep going. Eventually, so let's go pull back. So as I said, these are made in an IC fabrication facility. If you look at the solid state books and look at breakdown voltage in oxide, the typical number is 12 megavolt per centimeter with some kind of distribution around that. But people get this data based on making ASICs. And ASICs are small. And ultrasound arrays are big. And so, you know, when you make an ASIC, you make a million of them, and then you check, and sometimes you end up with a defect in oxide under one of them, and you throw that one away. So you have defects in the arrays are very large, and so you have to worry about that. It also is facility dependent. So in our facility, we design, instead of 1200 megavolt per centimeter, we design for maybe a couple of hundred volts per centimeter, just because it's dirty and some students, you know, don't wash their hands inside. I don't know. But, so that's what you have to worry about.
Thanks again.